Yeah, Bert, please go ahead.
Yes, well, very, very nice talk and very interesting work. I just wanted to clarify or understand one thing. So suppose I just consider the simple Laughlin nu equals 1/3 state, then because it depends a bit on what interactions you put in. But as I understand it, at least for Coulomb interactions, the graviton that you would be describing is embedded in a continuum of particle hole excitations, a continuum of excitations that I would make up out of pairs of rotons, magneto-rotons with total momentum k equals 0. So I would expect that it would be, you wouldn't get a sharp mode, but there would just, there would be some kind of spread in the a width to the graviton. Is that correct or not correct? And then
I think that when you I think that's correct in when you do the Raman scattering. I think that is expect that for the Laplace state nu to 1/3. I think that maybe the measurement of the Raman scattering for q equal to 0 will be will not be sharp. But however, you can check the excitation using numeric, and I think that at result I can check that. So
can I jump in? So actually the answer is yes, and I'm actually going to show some data tomorrow.
Okay, good, very good, thank you.
Okay, so the next question is by Hart Goldman. Please unmute yourself.
Yes, hi Dung, really nice talk. I have a couple of questions. The first is, how wedded is your approach to the Dirac composite fermion framework? It seems like you can do the same type of thing, adding a Haldane sector for HLR as well, although it's less clear to me that this type of thing would work for these like fractional Berry phase proposals from like Senthil and Chong.
Yeah, so for the case of the fractional Berry phase, we didn't consider. However, we also do some calculation for the SLR theory. And if you remember my previous with Son and Robert and Goga, we saw that if you do the if you calculate S4, the structure factor S4, you can see that it's also violates the Haldane bound. But now with extra Haldane sector, you can also satisfy the S4 for the SLR theory. And I think that you can repeat the same calculation for the SLR theory with the Haldane sector. About the same. Yeah. Thank you.
Yeah, and just one additional question is, so I don't know if you recall from our paper that we kind of put this zeta dependence in by hand. We didn't know that this Haldane sector was there, and we had guessed that the orbital spin had a particular value, and just plugged it in. So my question is, when you integrate out the Haldane sector, do you just get the effective action that
we
had,
get
or...
so basically the things that we do is that, so yeah, I think that it's Android idea, not my idea, because he already did this in the biometric theory.
I see.
So basically the thing is that in the low energy and also in the isotropic phase, because of this term, then basically the emergent metric also the same as the background metric. So from this thing, the spin connection here is also the same as the spin connection of the background metric. And so you have the ID omega here. And the ID omega here with the zeta here, then you fix the Wendish.
I see. But I guess my question was to get the, or maybe a sharper way of phrasing it is, in order to get the right answer for the static structure factor, does this require like additional momentum dependent terms that you might get on integrating out the Haldane sector, or
no, we don't need more. So for the calculation, to calculate the structure factor, also you can look at the paper by Sun and Andre. They also from this Lagrangian, they also calculate the S4. And I just even in my paper I also say that just look at Andre and Sun paper for the calculation. I just quote the result.
I see. I see. Great. Thanks.
Any other questions? Please raise your hand or just unmute yourself and go ahead.
Yeah, so basically, yeah, I want to emphasize is as we have this paper quite long ago, but recently Ed give us numerical results, so that's there's more than one spin 2 mode. And this is the reason that we decide to publish the paper, because even before that we also question what people think about the proposal. It's quite not natural, but Ed give us the confidence to do that.
Do you know what he calculated to make sure that there are 2 spin modes?
So he calculates the spectrum of the spectrum of the stress tensor, and he sees the peak at different frequency.
Two peaks, I see.
More than 2. So that's why at the end we put the K here.
Oh.
And another thing that I want to emphasize that the state nu equal to 2.7 is non-current. So that means you expect the currentlity with different, the stress tensor will have different currentlity. And also Ed also sees this in his numeric.
Duncan, please go ahead with your question.
Yeah, so essentially, I mean, if we get rid of rotational invariance issues in the thing, because rotational invariance is really not a fundamental. The only fundamental point symmetry in the quantum Hall states is inversion symmetry. Yeah. So in a sense, one should probably call the metric the shape field. It's the shape of the flux attachment. And there's also a separate shape. There's also a shape field for each Landau orbit, for that matter. They don't all have to have the same shape anymore.
Yeah. Yeah.
So if they can, so in this case, really, for every, meaning in Genedra's composite fermion thing, you've got a separate, basically you've got, if you take the hierarchy or the Jane sequence or whatever, if you've got more than one fluid in this hierarchy thing, there's a kind of shape, a shape mode for each fluid, right? So essentially, in some sense, if we stop thinking about as a metric as such, because it's the shape, the quadrupolar shape of the essential piece of each fluid. So somehow it's natural to have a shape mode for every generalized GMP type mode that you get in the
So I borrow your idea to have this proposal. So that's why we call this a Haldane sector.
Yeah.
Can I ask you a question, since you brought this up? When we did this bilayer study with Zlatka and others, this was precisely the thinking that I had. Each layer should have its own metric. And so we should find 2 spin 2 modes. And that's not what we found. Do you think if you just take a,
I would say each fluid,
possible bilayers,
each independent fluid component should have its own shape, right?
If I have 2 to 1 state, how many fluid components are
there? In 2 layers, I guess. The question is whether you can allow whether 2 fluids are rigidly connected or not, right? Whether you can allow, I guess if you have a proper 2-to-1 state, I guess both layers are combined in the same elementary object, right? But if I have a hierarchy type scheme, I suppose I can have the shape of the daughter condensate is now built out of excitations or quasi-particle of topological excitations of the parent state, and there's no reason that you can't have independent fluctuations of the shape of the daughter states. While in a 2-to-1, they really you really have a locking together of the particles in each layer, because each layer, the particle in layer 1 or whatever, forces a hole in a quasi hole of the other layer around it, right? So I would say in the 2-to-1 there is a single fluid, and while at least in a hierarchical idea of these things where you think that the 2/5 state is built out of it's not.
Well, I see what you're saying. What we found seems to agree with this. There is only one spin-2 mode in 2-to-1.
The question is whether you can, if you can independently shear. So basically things are error-preserving deformations, and the question is, how many independent components can you do an area-preserving deformation of it? It's clear that, at least in a hierarchical way of looking at it, you would not have if you could independently deform one fluid, a daughter fluid on top of a parent fluid, then you should have 2 modes, right? But yeah,
yeah. Okay, thank you.
Okay, maybe let's move on to the next session that will be chaired by GA1.